Looking at the achievements of civilization, have you ever wondered how unique we as humans are as a species? Think about it. What humanity does is complete madness for the other species on Earth. We speak words into some devices that hardly anyone understands how they work anymore. We broadcast this to the internet, which transforms it into information made of zeros and ones and delivers it to other computers. No other species can boast of such a thing. Or can it? Could it be that somewhere in the universe there are intelligent beings like us? In fact, before our star system was formed, others like it already existed. Some systems are relatively close to us in the Milky Way galaxy, and it's likely that life has already emerged in one of those star systems, similar to ours. What formula describes the probability of life existing on other planets? If you were an alien, would you want to contact Earthlings? And finally, why haven't we detected any signals from space yet? And are we using the right methods for this? Surely you know that so far scientists have not found any clear evidence of alien civilizations that could travel between galaxies. This is called the Fermi paradox. After all, during the existence of our galaxies, the migration of different species would have been quite natural. For example, there are about 400 billion stars in the Milky Way. Most of them have their own planetary systems with their own characteristics. In such systems, there are zones called habitable zones. Their conditions allow for the existence of a planet similar to ours. Thus, intelligent species like us could emerge there, although they might look different. However, even if life does arise somewhere, would it be able to reach us? To begin with, we can divide stars into 7 types by spectral class, and each of these types is further divided into 7 subtypes. Depending on these types, the appearance and behavior of the creatures living there will change, which gives us many possibilities for building theories. In addition to different types of stars, there is also a wide variety of planets. Some of them are called exoplanets. In the Milky Way, their number reaches 5 billion. And how many could there be in other galaxies? Some of the exoplanets may turn out to be suitable for life, while others have such hellish conditions that no living organism could exist there. We have already talked about such planets in more detail in our previous videos. In 1961, astronomer Frank Donald Drake created a mathematical formula that could be used to determine how likely it is that other intelligent species exist in the vastness of the galaxies. This is what the formula looks like. N stands for the number of civilizations with intelligent beings that currently exist. R shows the rate at which new stars appear. Average number of planet satellites is the average number of planet satellites. Probability that life can appear on a planet is the probability that life can appear on a planet. And probability that intelligent beings will emerge is the probability that intelligent beings will emerge there. Fraction of civilizations is the ratio of the number of planets whose inhabitants can make contact. And finally, L is the amount of time civilizations ready for contact exist. At first glance, this is a simple formula where the necessity of each component is beyond doubt. Despite this, the Drake equation has been the subject of lively discussions for many years. Scientists still haven't reached a consensus. Have we already mentioned that humanity has not detected any signals from other civilizations so far? Even if life exists on other planets, it might destroy itself if it doesn't make contact with other beings. For example, a civilization might wipe itself out with dangerous biological or nuclear weapons, which is quite likely since conflicts for various reasons have always been inevitable. Therefore, this civilization has limited time to make contact with another. Such beings would have to be much more advanced than we are to learn about our existence. In 1964, Nikolai Kardashev developed a method for measuring the technological development of a civilization, which is called the Kardashev scale. In this way, the scientist made an assumption about what alien civilizations might look like and how they might behave. He suggested classifying them into types depending on how much usable energy they can harness. Kardashev classified Type 1 civilizations as those using all the energy available on their planet. The second type includes those species that draw energy exclusively from the main star around which their planet orbits. But civilizations of the third type can use energy from everywhere in the entire galaxy. Astronomer Carl Sagan believes that we may reach the first type of civilization in about 200 years when we learn to use all the available energy on Earth. If organisms have the ability to use energy from the entire galaxy, then they can travel through space at speeds comparable to the speed of light. In some cases, they may even exceed it. If any civilization were able to pull off something like that, it would not go unnoticed by us. Nevertheless, we are still in the dark since no one is sending us a single sign. It is quite likely that the reason we have never heard anything about other civilizations is that we rely exclusively on radio astronomy methods to search for them. We have yet to find a star with strong radio emissions resembling signals from intelligent beings during this time. Perhaps our civilization is the only one among all the potentially existing ones that uses radio waves for communication. Does this mean that other beings use advanced technologies for communication? We shouldn't rule out this possibility because for us Earthlings, space is full of mysteries and unknowns. Some civilization might be using methods of communication that we simply aren't able to recognize. John Bolt proposed another theory, which became known as the zoo hypothesis. According to this theory, extraterrestrial civilizations exist, they know about our planet, but for reasons unknown to us, aliens do not make contact with us. They simply observe what is happening here. It's like a kind of zoo. But what is the reason for this? Probably we are not advanced enough for these civilizations. We are simply not interesting to them and cannot offer anything new. This version could also explain why we still haven't been able to detect anyone. Other civilizations may simply not want this, only observing the events that happen on our planet. Perhaps these intelligent beings will reveal themselves when we experience some significant event. For example, when we make substantial progress in space science and finally move on to the dark forest theory. It got its name from the science fiction book by the Chinese writer Liu Cixin. He writes that all intelligent beings have one goal: to survive, and we don't know exactly what they want. We also can't know for sure whether communicating with other forms of life would pose a threat to us. Liu Cixin describes our universe as a dark forest, full of the unknown where you never know what awaits you next. Danger lurks everywhere for us. Other civilizations might simply be afraid that we could harm them, which is why they don't respond to the signals we send. Whether these theories are true or not, at this point we can't say for sure. Be that as it may, if other civilizations do exist, they might have different feelings toward us, ranging from caution to condescension. Let's say, they would probably be amused by the fact that we, perhaps not even having reached their level of development, consider ourselves an all-powerful and exceptional form of life. Now look at this photo. This is one of the areas of our vast cosmos that was captured with the help of the Hubble telescope. This isn't a very large part of the cosmos. It contains only about 10,000 galaxies. But just think about how much remains unexplored even in such a tiny area. It seems absolutely foolish to call ourselves the only intelligent beings, because we can't even know that for sure. All the signals we send just go nowhere. Maybe someday we'll get an answer, and a whole new era will begin for all of humanity. A few centuries ago, we had no idea whether the sun revolved around other planets or if it was the other way around. You'd think there would be fewer mysteries now, but that's not true. The more we learn, the more questions we have, and finding answers to them turns out to be difficult. We know that in the universe, something is always revolving around something else. The planets of the solar system revolve around their main star, the sun. The sun, in turn, revolves around the center of our galaxy, the Milky Way, and the galaxy revolves around the center of mass in the Virgo supercluster. This object is one of the elements of the Laniakea supercluster. There is no single center around which all objects revolve. They all move toward a center called the Great Attractor. Opposite, it is a mysterious object that scientists still cannot figure out, the dipole repeller. In this part of space, there is an absolute field, the void. Such places have been called voids. To make it clearer for you, this image shows countless galaxies, and the dark areas between them are those very voids. The cluster of a large number of galaxies on the left side of the image is called the Great Wall of Hercules Corona Borealis. We still don't know the full variety of objects that are out there. Let's go back to this image again. You see, there are many thin filaments, but what connects them together? That's exactly one of humanity's mysteries. The materials that make up superclusters don't have enough gravity to hold everything together, so that option's ruled out. This issue has long troubled scientists. Back in the 1970s, they tried to figure out how the rotation speed of stars in a galaxy depends on their distance from the center. You can calculate the speed if you know the mass and radius, but the results they got just didn't match reality. The speed of the elements at the edges of our galaxy was much higher than expected. It's quite possible that there is still some unknown matter in those areas that we've been unable to detect all this time. Scientists have named it dark matter. It's worth noting that it's not black in color, as you might think. It's better to call it invisible. It doesn't have the ability to absorb or emit light. Objects like X-rays, for example, pass through dark matter without any obstacles and don't interact with it at all, as if nothing is happening. We know that the distribution of dark matter throughout the universe is uneven. In some places, there's more of it, and in others, there's less. In the constellation Coma Berenices, they found a galaxy that is almost entirely made up of dark matter. Precisely because its distribution is uneven, a multitude of galactic filaments have formed. Elements surround dark matter because it seems to us that these are voids. But the question of what this strange substance actually is remains open to this day. Scientists know very little about dark matter. They are trying to learn more about the nature of this material, but each time they become more convinced of its exceptional and unique qualities. At the moment, we know for sure that dark matter cannot be called antimatter. Antimatter is a substance that consists of antiparticles, which are the counterparts of the particles that make up ordinary matter. Dark matter, on the other hand, interacts with ordinary elements through boundaries. In the case of antimatter, contact with other materials can lead to an explosive reaction, up to the release of nuclear energy. It was previously assumed that there are relatively small but very massive objects in dark matter, or, scientifically speaking, massive astrophysical compact halo object. They have very strong gravity, and under their influence, even the bending of sunlight can occur. Neutron stars and black holes can be classified as MACOs. For example, if there really were such supermassive compact objects in dark matter, there would be countless cases of sunlight bending and similar phenomena. Now let's touch on quantum physics. Many people consider this science controversial, but nevertheless, it also has plenty of supporters. In quantum physics, there is the so-called Standard Model. It contains 17 elements of the universe. If you add an 18th particle to it, everything will simply fall apart. As you can imagine, dark matter is not on the list, so researchers have to study this substance basically without any foundation. So far, they haven't been able to find the particle that should make up dark matter. It has, you could say, been given the name weakly interacting massive particle in absentia, which stands for weakly interacting massive particle. We know for sure that it must be heavy and slower compared to other particles. Yes, for now, we don't have much information. Maybe the sun will help us learn more. Yes, you heard that right. Our main star is passing through a cloud of dark matter, capturing particles with its gravity. There is a theory that the speed of WIMPs will be too low to resist the sun's gravity. In that case, they would just get stuck somewhere in its core. There could be quite a large number of WIMPs there. In that case, under high pressure, they will release lighter particles by annihilating each other. The sun throws neutrinos into space in huge quantities. This is exactly the element that passes through our bodies from head to toe. Such particles are no different from each other, but if they interact with dark matter, it will be immediately noticeable. The energy level of neutrinos will increase tremendously. Right now, neutrinos are detected using devices that are placed deep in water. There is another theory. At the outer edges of the galaxy, there could very well be primordial black holes that are up to 14 billion years old. Some scientists have suggested that such objects could serve as a source of energy for us. Their power could reach 10 million megawatts. That amount would be enough to supply all of us with electricity. The only problem is how to make a black hole work for us. Some scientists suggest even more provocative theories about dark matter. Its creation may not be due to a single particle, but rather an entire system of particles. The web of galactic filaments matches the shapes of dark matter, meaning these particles could create a real cosmic mirror world. Such a system could have opposites to ordinary elements, dark neutrons, dark electrons, and so on. There is a hypothesis in the scientific community that at the early stages of the universe's development, some particles from the ordinary state were able to transition into dark ones. In the future, we will surely get more information about this. The Sun, along with all its planets, moves around the center of the Milky Way galaxy. That's why every second our bodies collide with dark matter particles. Not all of them collide with atomic nuclei. Hundreds of thousands of particles get lucky each year. Dark matter is actually everywhere. So far, we haven't found a dark planet, for example. Otherwise, there would be a lot of unpleasant moments for us, a lot. They would end up in the center of the planet, where gravity wouldn't let them out. Many of these assumptions seem kind of fantastic and unrealistic to us, but we haven't discussed one important question yet. The thing is, besides dark matter, there is also the so-called dark energy. What is it? This is the energy that causes the universe to expand at an ever-increasing rate. Dark energy has little in common with dark matter, except that both are actually invisible to us. We know for sure that dark energy has mass. It's an inherent part of space. It's everywhere, even in a vacuum. Dark energy causes there to be more of it everywhere, thus expanding the universe. This process is happening faster and faster each time. Dark energy is kind of the foundation that holds dark matter, and it makes up 68% of the entire cosmos. That's more than twice the amount of dark matter. So according to modern understanding, the universe consists of 25% dark matter, which we detect thanks to gravity, as much as 70% dark energy, and only 5% ordinary so-called baryonic matter, which makes up all observable objects. That means the entire world we can see with our eyes is only 5% of the universe. Incredible, isn't it? I think you remember how as a child you looked at pictures of the starry sky in encyclopedias and thought there was nothing between the stars. But it turned out that's not the case. Everything in the universe is invisible to us. It seemed that just a few centuries ago we didn't know whether the Earth revolved around the sun or vice versa. But now we're interested in more fundamental questions, because the universe loves to constantly surprise us. Remember the scene that each of us has seen many times, though fortunately not in real life. But even watching it on a screen, a person inevitably feels genuine horror. We're talking about a nuclear explosion, Tom. The brightest, most ominous orange mushroom cloud rising above the Earth, and killing everything within a radius of several hundred kilometers. What precedes this catastrophe? The natural detonation of an atomic or hydrogen bomb. And now, attention. Here's a question. How identical are these concepts? Are there any differences between them? Let's figure out the problem right now. Simply put, the atomic bomb is the predecessor of the hydrogen bomb, which is more modern and technically advanced. The main differences between them are in the detonation process, but not only that. In general, a theoretical comparison of these types of bombs on paper is not that impressive, since the potential energy of fission of uranium-235, which is involved in the detonation scheme of an atomic warhead, and the fusion of lithium-6 deuteride, an essential component of a thermonuclear explosion, differs by about 3 times. But in practice, it's like comparing paradise with Dante's Inferno. Let's start from the beginning. The shape and size of the mushroom, the differences begin with visual characteristics. The explosion of both bombs is accompanied by the appearance of a recognizable cloud-like mushroom-shaped silhouette. But that's where the similarity ends. The explosion of an atomic bomb can be recognized by its relatively modest cap and thin stem. With a thermonuclear bomb, the cloud is much larger, the stem much thicker, and the mushroom's height can be truly terrifying. The difference in processes. An atomic bomb is based on nuclear fission, while a hydrogen bomb is based on fusion. Simply put, the processes can be described roughly like this. Fission is the splitting of the nucleus of a heavy chemical element, for example, plutonium or uranium. First, the charge is detonated, after which the isotopes rapidly decay, leading to the destruction of atomic nuclei. As a result, a tremendous amount of energy is released, and the infamous nuclear mushroom cloud appears. The entire process takes only a fraction of a second. It was this very chain reaction that was at the core of the bombs dropped on Hiroshima and Nagasaki back in 1945. Uranium-235 used in atomic bombs doesn't fully undergo fission. For example, Little Boy, which killed hundreds of thousands in Hiroshima, contained 60 kilograms of this element, but just 700 grams of uranium. 235 underwent fission. This means the atomic bomb's conversion rate was extremely low, about 1%. In terms of resource inefficiency, it can be compared to an outdated and uneconomical incandescent lamp, which also has an efficiency of about 5%. By the way, the maximum possible yield of an atomic bomb is limited to 800,000 tons in trinitrotoluene equivalent, but that's just in theory. A yield of 500,000 tons is already extreme. And what about the hydrogen bomb? What characterizes how it works? The thermonuclear process is more complex than the previous one because it involves 2 stages, fission followed by fusion. Essentially, a hydrogen bomb also includes an atomic bomb, 2 warheads in one package. First, inside the hydrogen bomb, the nuclei of lithium-6 deuteride split, instantly breaking down into tritium and helium. After that, fusion comes into play. The colossal temperature of several million degrees creates the conditions for the nuclei of the resulting elements to fuse together, which leads to a sharp increase in heat and a powerful explosion. At the same time, far more energy is released than in an atomic bomb detonation. Power indicators? Let's conduct a comparative analysis using the example of the most deadly and powerful bombs ever created by humanity. First of all, let's pay attention to the atomic bomb detonated in 1952 during the American Operation Ivy. Its yield was 500,000 tons in trinitrotoluene equivalent. Before stating the parameters, it's worth making a brief theoretical digression. How exactly is the power of bombs measured? The standard classification is generally used. The destructive power of an atomic bomb is measured in kilotons, while hydrogen bombs are measured in megatons. 1 kiloton is equivalent to 1,000 tons of trinitrotoluene, but with 1 megaton, it's a different story. It's equivalent to a whole million tons of trinitrotoluene. Do you feel the difference? Basically, a thermonuclear explosion combines two colossal processes. Its power is theoretically limited only by the amount of available components. It's time to demonstrate what these calculations look like in reality. So, meet Mark 18 with a yield of 500 kilotons. The fusion process did not participate in the detonation. Therefore, the bomb, which measured 3.2 by 1.5 meters and weighed 4.5 tons, became the most powerful purely nuclear weapon. First tested in 1952 at the Tola Eniwetok test site. The destructive effect of the bomb turned out to be similar to warheads created earlier. So although the weapon began to be mass-produced later, the use of Mark 18 was abandoned. And now freeze. Before you is the world's most powerful thermonuclear bomb. The Union of Soviet Socialist Republics is AN 602, or Tsar Bomba, listed in the Guinness Book of Records as the most terrifying weapon ever detonated. The test of this monster was carried out in October 1961 by dropping it from an airplane. The Tu-95V was used as the bomber. The power of the Tsar Bomba was 59.8 megatons. Although Nikita Khrushchev initially tasked the nuclear physicists with designing a hydrogen bomb with a yield of 100 megatons. But after weighing the risks, they abandoned this idea. Device 602 was tested at the Sukhoi No site on Novaya Zemlya. The consequences of the explosion were so impressive that no one has been able to surpass them to this day. The shock waves circled the globe 3 times. The flash was visible from a distance of 1,000 kilometers, meaning it was clearly seen in Alaska, Greenland, and Norway. And the mushroom cloud was seen from 800 kilometers away from the test site. Moreover, on Dixon Island, which is located 780 kilometers from the explosion, all the windows in the houses were blown out. The width of the upper tier of the mushroom cloud was 95 kilometers, and it rose to a height of 67 kilometers. 40 minutes after the explosion, the atmosphere was so ionized that there was significant radio interference. As for the radiation background, it increased only slightly, especially when compared to the catastrophe brought to Japan by the bomb's little boy and Fat Man. Interestingly, one of the unofficial names of the AN 602 is Kuzkinamat. Legend says Khrushchev was referring to the Tsar Bomba when he angrily threatened the United States with Kuzkinamat, banging his shoe on the podium. To summarize the above, it can be stated with confidence that thermonuclear weapons are currently the deadliest and most destructive weapons in the arsenals of the nations on planet Earth. The leaders of some countries claim that by possessing a significant nuclear arsenal, they gain the ability not only to effectively defend their borders from external attacks, but also to influence political decision-making. And what do you think? Is it really necessary to obtain a license for mass murder in order to achieve peace? Share your thoughts in the comments, let us know which topics interest you, and stay tuned for updates on the channel. There's a lot of interesting stuff ahead, but what's really important for the channel is your engagement. What kind? You might ask, and I'll tell you. It's your big, hefty electronic like, which looks like this and is right below this video. If you can collect 20,000 of these electronic thumbs, I'll release the sequel right away. Do it, and the universe will definitely reward you.